Hi, in this lecture video, I will be discussing the Haloalkane functional group. So first, I'll go over some basic descriptions and introductions to the Haloalkane, and then I'll be discussing the physical and the chemical properties of Haloalkane. So first, let's get started with the Haloalkane. As its name implies, haloalkane are a functional group that consistent of an hydrocarbon chain, so basically an alkane, and a halogen bonded to it. So for an example, here we have a hydrocarbon chain, and now we have X, and X here is the halogens. So X can be fluorine, chlorine, bromine, or iodine, any of this halogen, and then this will then make up this haloalkane functional group. Now, each of the position on the hydrocarbon chain can be labeled with special terminology, so that way we can refer to them easily. And the most important one is this carbon right here, that is directly connected to the halogen. And this is called the alpha carbon. So again, the alpha carbon is basically the carbon that is directly bonded to the halogen. And carbon that are then bonded to this alpha carbon right here can be on the left or on the right, and both of them would then be referred to as the beta carbon. And then the carbon that is then bonded to the beta carbon would then be called the gamma carbon. So this is how we can label each of the position on the haloalkane. And the reason why we label this is that because later on, when we are discussing chemistry, it will be convenience that we are able to refer to each of this position right here easily. And now, haloalkane can also be classified as primary, secondary, or tertiary based on the number of alkyl groups that are connected to the alpha position. So for an example, here will be the alpha carbon, and in this case, there's one alkyl group connected to this. So in this case, this will be classified as a primary alkyl halide, or a primary haloalkane. And here will be a secondary alkyl halide, because again, this is the alpha carbon, and it has two alkyl groups connected to it. And similarly, here will be a tertiary alkyl halide. And also recognize that in all of the haloalkane, the carbon that is bonded to the halogen, it is all sp3, regardless of whether we have primary, secondary, and tertiary. This carbon right here are all sp3. And now, let's now discuss some of the property of the haloalkane functional group. And the one that is most important that we need to know would that be the carbon and the halogen bond. This is a polar bond. So the bond is polarized. And what this means is that the electrons that are found in this bond right here are not shared equally between the carbon and the halogen, but then are shifted to one atom over more than the other. And this is due to the electronegativity of the halogen. It is much greater than the electronegativity of the carbon, so therefore this bond right here is polarized. And of course, the different halogen have different electronegativity on them as well, with fluorine being the most electronegative. So we will then see that the bond between carbon and fluorine will be the most polarized bond. And here is a diagram that shows how the orbitals are overlapping to make up this carbon halogen bond right here. The carbon is using an sp3 orbital, and the halogen is using a p orbital to form this bond. And here will be the electron that share between these two atoms. Now, knowing and seeing that the CX bond here is a polarized bond is really important in order to understand the chemical reactivity of haloalkane. So this alpha carbon right here is very, very partially positive. And this is why that it will be a great electrophile. And therefore, it be subject to attack by a nucleophilic species or a nucleophile in chemical reactions. And now, the bond strength between the carbon and the halogen plays a very important role in the reactivity of the different haloalkane. Because the longer this bond, then the weaker it would be, and therefore in chemical reactivity, it may break easily. So therefore, the bond length here is then directly correlate to the chemical reactivity and how easy it is to actually come in to attack this carbon. Okay, so as we can see, the larger, as this halogen get larger, it will become bigger, and the overlap between this orbital would also become weaker as well, making this bond right here becoming weaker. So weaker bond as the halogen get larger. And for an example, down here are some of the data that show us the bond strength between the carbon and the halogen bond. And as you can see, so iodine is the biggest one, and we can see have the highest bond length and now the weakest bond strength. So this is a very important physical property that we need to keep in mind in order to understand the reactivity of the different haloalkane. Okay, and this diagram right here is showing the electrostatic potential map of the different haloalkane. And in this case right here, we can then see that the iodine is the biggest one, while the fluorine is the smallest one. And now, notice the electropositive region on this carbon right here. So we can see, even though it may be a little bit difficult to see, but then the carbon on the side of the carbon that is connecting to the iodine, this is somewhat a little bit more partial positive compared to the one that is connecting to the fluorine. And now this may sound to be kind of counterintuitive a little bit, but it actually makes sense. And the reason is the following. First of all, we see that this doesn't make that much sense because fluorine is more electronegative than iodine. So it would then make sense that fluorine will be inductively taking an electron away from the carbon, making this become more partially positive. However, the bond between carbon and fluorine, this is a strong bond. So therefore, the tendency of this bond right here being broken would then be less. And because this is a stronger bond. And now, at this bond right here, so that this bond strength and this bond length right here also play a very important role why this carbon right here would then be less positive. In the case that we have a bond between carbon and iodine, this is a longer bond. And being a longer bond, this bond right here may break easily. And when this breaks easily, then there is a greater chance where the iodine can break up and take in the electron with it. And when the iodine breaks up with the electron, we will have iodine, and that would then be more stable compared to the fluoride. So therefore, this iodine right here will have greater tendency to take the electron away from the carbon by breaking this bond and fall off with it. So in a way, this will be a better leaving group. And this is why that it will make this carbon right here becoming more partial positive. So again, this is a very important thing that we need to be able to understand. And so let's summarize this. So we can see that when it comes down to the bond between the carbon and the halogens, then the fluorine would have the shorter bond, and the iodine will have the longest one. But when it comes down to the bond strength, it will be the opposite. The bond between carbon and fluorine will be the strongest, and the bond between the carbon and iodine will be weakest. And now the carbon on bonding to the iodine will be the better electrophile. And this is kind of how it would go in terms of the reactivity of the different alpha carbon that are connected to different halogen. Carbon connecting to iodine will be better electrophile compared to carbon they connected to bromine. And next chlorine, and lastly it would be the fluoride. So in this case, this is a direct correlation to the bond's strength. The stronger the bond, then the less electrophilic this carbon would be.